In this tutorial, I would like to show you how you can use the Procedural Content Generation framework that was released with Unreal Engine 5.2 to create a forest environment. In the first part, we will learn about the basics of the PCG framework and explore various techniques for the creation of environments, like density filtering, spline sampling, and mesh sampling. In the second part, we will then start in a new scene from scratch and build the procedural forest environment that you're seeing here. To start using the Procedural Content Generation framework, you need to activate it under Plugins. Go to Edit, Plugins, and type Procedural. Then tick this checkbox here, Procedural Content Generation Framework. And you can also already activate the Procedural Content Generation Framework Geometry Script Interop, which we will be using later on for having access to the mesh sampler. After ticking these checkboxes, Unreal Engine will ask you to restart the engine, so please go ahead and do so. In order to use the Procedural Content Generation framework in the scene, we need to do two things. We need a PCG volume and connect this PCG volume with a PCG graph asset. So I'm just gonna delete this test setup here and build it from scratch. I start with creating a PCG volume, just type volume here, then PCG volume pops up. It's gonna put it roughly in the same spot. Get a bit bigger. Okay, now that we have the PCG volume in our scene, we need to assign it a PCG graph asset. Go to your content browser. I have this folder here under PCG tutorial, right click, type PCG, and create a new PCG graph asset. Click the PCG volume in your scene and go to the PCG component under details. And here you will see the slot for the PCG graph asset that you can just drag in here. Right now, this input type is defined as actor. What we actually need for this tutorial is to set it to landscape. After doing so, just double-click the PCG graph asset and it will open up the empty PCG graph, which just holds an input and output node. So for this first PCG setup, we are just going to create a surface sampler node. Right-click and type surface sampler. And then we're just gonna select the surface sampler node and press D. And also click generate on your PCG volume under PCG component. So this is the base setup for the procedural content generation. What you can see here is points being sampled on the landscape. So let's open up that graph and change some of these settings. Under points per square meter, you can basically see the sampling density on the landscape. So if we increase the points per square meter, nothing happens yet because all of these settings here are depending on each other. The point extents are right now 100 by 100 by 100 units. So if we actually want to have a denser grid on the surface of this landscape, we also need to decrease the points extents. And as you can see now, we are sampling more points on this landscape. It's a random sampling, so if we change the random seed, you will see that the distribution of the point sampling changes on the landscape. As you can see, these points are currently oriented to the normals of the landscape that they are sampled on. If we want to change the transform of these points, we can add a node that's called transform points. And then we can, for example, change the offset, rotation, and scale of the points. Currently, the debug flag is still set on this surface sampler, as we can see with this turquoise point here on the node. So if we want to actually debug our most current node, which is the transform points, we need to right-click it, press and check this debug checkbox, or press D, or even better, press Ctrl-Alt-D. What this does is moving the debug flag from one node to another. So as you can see, at first we had this surface sampler being debugged, and now we're moving the debug flag to the transform points. We don't see any change yet because it's just like being set on the default settings right now. So in order to see a change, I'm just gonna apply some more randomness to the rotation. These values go from a minimum value to a maximum value and are distributed between these values randomly. So all of these points are now being rotated on the z-axis between 0 and 360 degrees. And we can also, for example, change the scale of the points and randomly scale them between, let's say, 1 and 2. And now you can see that we have a random distribution of randomly scaled points that are also being rotated between 0 and 360 degrees. Most of the time, we don't just want to use the full set of points that are being sampled on the landscape, but we want to filter them in some way, sometimes based on the properties of the landscape or on other parameters. I'm actually not going to create a new volume here because the process is exactly the same. Just make sure if you create a new one to set the input type to landscape in the PCG component settings. So what we can see here is, if I set the debug flag to the surface sampler, we have a certain density of points, and the point density is being set randomly by the surface sampling node. A density of 1 is white and a density of 0 is black. And now what we can do is we can add a density filter node after this to filter out the points based on a certain lower bound and upper bound. So in this case, we would be only showing points with a density between 0.5 and 1. Let's move on and actually spawn some static meshes on these points. So first we're gonna add a surface sampler, put it into debug, maybe set the point extents to 50 by 50. Then apply some density filtering. And after the density filter, add a static mesh spawner. In the static mesh spawner, under mesh entries, we can create a new entry, unfold it, and then drag one of our tree assets into this slot here. Now what we can see is that the trees are being spawned in the location of the points and also follow the orientation of the points. Let's actually turn off the debugging for a second. So what you can see here is that, especially on the slopes, the orientation is really unnatural because trees tend to grow upwards. So we might want to adjust this. Before the static mesh spawner, I'm going to add a transform points node. And I'm going to change the rotation to absolute rotation. And now you can see that all of the trees are pointing upwards. To create a little variation, I'm actually going to change the rotation on the X and Y axis in a range from -5 to 5. Now what you also might want to do is offset the Z location of the trees, so you don't see the open end of the mesh here. Just going to change the offset to -10. And then what you would do to create variation in your spawned assets is to add further assets, static meshes, to the mesh entries array. So I'm just going to click the plus button here and add some additional tree assets. Now we can increase the density of the points. Maybe it also adjust the rotation a bit to make it a bit more diverse. So this is a very basic setup for spawning static meshes on the surface using surface sampler, density filter, and a static mesh spawner. Let's move on to the next topic, which is bounds and self-pruning. In the PCG framework, the bounds define how much space your sample points take up in the scene. And you can then modify these bounds to fit the mesh that you're actually spawning. And then use a node that's called self-pruning to prevent intersections between the actual meshes. So let's have a look at this node tree here. I'm going to disable all these nodes by selecting them and pressing E, which stands for enable and just toggles, enables, disables the nodes, which is a very handy shortcut. And now what we can see is that the surface sampler spawns these points with a base unit bounce size of 1. But sometimes a bounce size of 1 is not enough for covering the actual extents of your spawned meshes. So what we can do in this case is add a bounce modifier to change the extent of the spawned points and match them to your static meshes. So let's enable the bounce modifier here and also the static mesh spawner. And go in the bounce modifier, and I just changed everything from 1 to 3. So instead of 1 unit, all of the points are now taking up a space in the scene of 3 unit on all axes. Now what we can do with these changed bounds is add a self-pruning node after this. Just to show you the difference, enabling and disabling it. For example, here we would have some intersection, and with the self-pruning it's gone. So this is how you can use the bounce modifier and self-pruning to fix static mesh intersections. Now let's move on to the next topic, which is also touching the bounce modifier, but focusing on fixing intersections between different kind of meshes. As you can see in this setup here, I have 2 kinds of meshes, rocks and trees, and there are no intersections between them. And then there's also another type of mesh, which is just a test cylinder. And if I move this cylinder in the scene here, you can see that no trees are being spawned where the cylinder is currently located. It's all happening dynamically. So first of all, we're starting with the surface sampler as usual. I'm gonna set this in debug, change the point extents, maybe even smaller, to 25, and increase the density a bit. And now I'm just gonna already add a static mesh spawner. And gonna add my first asset here, which is a tree. Then we're gonna repeat the same process as in the other node graph. So I'm gonna add a self-pruning, but it has to be before the static mesh spawner, of course. And also we wanna again change the point extents, although it's fitting quite well. It depends how dense you wanna put them. Of course, if you would like to have some spacing between the trees, you can modify the bounds, or we can just keep it as default here because it seems to be working quite well. So next we are gonna add some rocks. For this, I'm creating another surface sampler. Put it into debug, turn off the trees for now, and add another mesh spawner. And in the mesh spawner, under mesh entries, I'm gonna drag a rock asset. In this case, I'm using one from Quixel Megascans, but you can use any kind of rock asset here. And now if we turn off the debug flag, we see that the extents of the points here doesn't really fit the actual mesh. So in order to change this, we're gonna add a bounce modifier in between. Set its debug flag, and now try to adjust the bounds of the points to the actual mesh. I'm gonna try 0.6 on the x-axis, 0.3 on y. Yeah, that's pretty close already, so maybe 0.65 on x and 0.35 on y. That's close enough. And the z-axis is actually not important here right now, so I'm gonna leave it like at 1. Now, if we want to change the overall scale of these points or of the rock assets, we're gonna need to add another transform points in between. I'm gonna change the scale, or I'm gonna create a random scale between 1 and 3 here. And by the way, as you can see, by default, uniform scale is ticked. That means that it doesn't actually matter what you put in the Y or Z slot here, Z-axis slots here on the scale min and scale max. So only the X-axis slot will influence the overall scale, and the other parameters will adjust based on this X parameter. And I'm also gonna change the rotation and randomize it a bit, and then turn on the trees again. And as you can see, you have a lot of intersections between the rocks and the trees. And now we're gonna fix this by adding a difference node in between the self-pruning and the static mesh spawner of the tree. Just gonna make some space here and add a difference node and change the density function parameter to binary. And then I'm gonna drag from the output of the transform points to the second slot of the difference node. And as you can see, this fixes all the intersections between trees and rocks. Now you still might get self-intersections of the rocks because we didn't add any self-pruning. Here's one, for example. If we change the seed of the mesh sampler a bit, maybe we will find them in other positions or not at all. Right now that seems to fix it, but of course if we want to make sure that the rocks are not self-intersecting, then we can also add another self-pruning node here for the rocks. So right now that's enough for me, and we move on to actually also excluding these debug cylinders here. In order to do this, we need to add a certain kind of node that's called getActorData. And to prepare this kind of technique, you need to actually give these cylinder actors a tag. Select them in the outliner, search for tag, and I called this tag PCG Exclusion. I'm gonna copy it, also check that it's available on the other cylinder, and then go back into the graph. Under getActor, we actually select under actor filter all world actors, and then actor selection by tag, and paste the tag here. Now what we need to also keep in mind is that we want to select multiple actors because we have multiple of these cylinders, so make sure to tick this. And then what we can do is we can just drag the output pin of this getActor on the same input slot of the difference node, and the PCG network will add up all these different inputs and combine them to a combined exclusion or difference. So this should already be working. Let's verify it by moving the cylinder around, and yeah, as we can see, it's working. So since we also already select the select multiple tick box here, we can just duplicate the cylinder and it will automatically exclude all the cylinder instances in the scene. Now, of course, we could also do the same with the rocks, and we would just copy this difference node here. And put the output of the get actor data also here. So as you can see now, it's excluding both the rocks as well as the trees from the cylinders in the scene. You always want to make sure that you have some differences in your PCG graph, so you're not spawning rocks into trees or other kind of foliage. For now, let's move on to another technique, which is slope filtering or density filtering based on slope. It's a really simple graph. We just have a surface sampler as usual and a particular node that's called normal to density. In here, we define a normal that we want to compare the points against. In this case, it's just the upwards pointing normal. And now it's taking basically the normal of the landscape, comparing it against this normal that we define here, and setting the density based on this comparison. And then we can apply a density filter to it and filter out the nodes that are fitting to the normal that we define in a certain boundaries. So with this, for example, we can filter out points that are just on the slope, as you can see here, or points that are just relatively level, or even just points that are on the edges of the slope, just by changing the lower and upper bounds. And for example, this last variant could be used to spawn cliff assets just on the downside of the slopes or on the edges. Basically, it's a very handy technique. So let's move on to spline sampling. As you can see, you can use a spline and sample points along it and then spawn static meshes on the spline curve. If you change the spline, it's gonna all adjust dynamically. You can add points to it and it's all gonna adjust. So I would like to set this up from scratch and show you how to do it. In order to sample splines in the PCG graph, you can add a spline component to the PCG volume actor. So just select your actor, click add, type spline, and add it here. Then open up the graph. And now what we need to do is get a spline data node and keep the actor filter selected as self, which is the default. Then after, we're gonna add a spline sampler node and put it into debugging. Then go a bit closer here and add some points to the spline. Oops, I actually duplicated the spline. I just wanted to add some points here. Okay, there you go. And then we also need to click generate if you don't see anything yet. All right, this seemed to change something. What's happening here is that the points are actually being displayed as stretched along the spline, but strangely, this doesn't actually seem to change the scale of the assets that are being spawned on it. It just seems to be a display issue, and I don't know if it's intended like this or if it will be fixed in future releases, as the PCG framework is also still an experimental feature of Unreal Engine. So I'm not exactly sure about it, but it's definitely working, and you can just ignore the stretched debugging view of the point extents here. So all I'm going to do is just add a static mesh spawner, add some mesh to it, and there you have it. then what we can do is to adjust the sampling of this spline is to actually subdivide it. So subdivisions per fragment, set it to 5. And as you could see here, because the segments are closer together here, you're actually going to get 5 subdivisions in this segment and also 5 subdivisions from this point to this point. So depending on how uniformly your points are distributed on the spline, you will also have a density of sampled meshes accordingly. If you would like to change this behavior, you can change the mode in the spline sampler from subdivision to distance, and then adjust the distance increment according to your needs. In this case, it was set to 50, and based on the distance increment, we are changing the sampling density along the spline. In the previous example, we were spawning points on the spline itself, and now we want to look into how we can spawn points on the inside of the spline or on the area defined by the spline. So let's open up this graph. The setup is almost completely the same. We get the spline data with the actor filter self, but then on the spline sampler, we're going to change the dimension property from on spline to on interior. Let me actually debug this. So as you can see, this spawns a bunch of points on the interior of the spline. And all I did then was apply a random density noise, then a density filter to filter out some of the points, and then just connect a static mesh spawner to spawn the tree assets. Now, what's also worth noting is that you can define an additional density falloff by adding some keyframes to the interior density falloff property on the spline sampler. So just add some keys here and define the falloff. Now, for example, the density would go from full density on the outside of the spline to a lower density on the inside of the spline. And we can use this later on to create some variation in our assets, like scaling them accordingly or applying other changes to the meshes based on this density falloff. Now let's move on to some interesting use cases of spline sampling. For example, you can use spline sampling to automatically exclude water bodies from the foliage spawning, and I would like to show you how to do this. To follow along here, you need to activate Unreal Engine's experimental water plugin, which you find under Edit, Plugins. Just type water, tick this checkbox, and restart the engine. After restarting, you can just edit a water body by typing water and adding a river. I already did this here, so I'm just going to open up this graph and start building it from scratch. So in order to get the spline of this river, we're going to use the getActorData node and set the actor filter to all world actors, and then change the actor selection from by tag to by class. Under class, we're going to just type water and select the water body river class. Also, we can again check the select multiple if we have multiple water bodies that we would like to filter. After this, connect it to a spline sampler and put it into debugging. Again, what we can see here is that the points are being stretched along the spline based on the subdivision of the spline sampler. So what we want to do now is change the extents of these points to then use them as a difference on our foliage assets. So I'm actually gonna create a transform points node, set the debugging flag, set the scale to absolute, and also increase the subdivisions per segment to maybe 20. And as you can see here now, you have a lot of points along the spline. They are very tiny because I just changed the scale to absolute scale, because now I want to change it manually to fit the width and depth of this river. We also need to untick the uniform scale checkbox because we want to actually set all the scale properties individually. So let's start with the x-axis. I'm going to try a value of 500 here. We actually need a bit more, maybe 1000. Here you can see the extents of the points. And on the y-axis, we're going to try 500. That's already a bit too much, maybe. Depends. 350. And then also increase the x-axis again, maybe 1200 to cover the whole river. And in this case, we also need to set the z-axis, and you will see y in a bit. For now, let's just add a surface sampler, connect it to the output of our input node, and put it into debugging. Change the points extents. Slightly increase the density, and add a static mesh sampler, a static mesh spawner. Now we also need a difference node. Again, set it to density function binary. And now connect the output of your transform points node from the spline sampler of the river to the difference node of the trees. Let's debug again the spline of the river here, or the spline sampler of the river. So as you can see here, it's kind of starting to work. Some of the trees are definitely getting excluded, but not all of them. And the reason is that the extents of this spline sampler points are not reaching the bottom of the river. So we actually also need to increase the scale on the z-axis to maybe 100. And now we can also see that we went a bit too far, or we went a bit too wide on, I think it was the y-axis. So let's decrease it to 250. Yeah, that should do it for now. Let's turn this off. And let's change a bit the seed of the surface sampler. Maybe also make it a bit more dense. And there you go. Your river is dynamically excluded from the foliage spawning. Now if I select the river, water body river, and if I change the points here, let's say I want to add another point in between here and actually make it flow like this. The PCG graph is adjusting accordingly or the PCG spawning is adjusting accordingly based on the rules you set in the graph, and everything is working dynamically, which I think is really nice. It's a very similar setup for the lake, so I'm just going to go over it briefly. In the graph under Get Spline Data, instead of selecting the water body river, you're going to select the water body lake. Then adding another spline sampler. Just going to turn off the outputs here for now. And debugging the spline sampler. Then what you can see is that these points actually appear on the surface or even below the lake. So I'm just transforming the points here and then using a node that we haven't used so far, which is the projection node. With the help of this node, we can take the sampling points from our lake and reproject them on our landscape. And this is possible since in the PCG component under input type, we still have landscape selected. So we can just connect the input node here to the projection target, and it will project the points on our landscape. Then let's enable our tree static mesh spawner, increase the density of the trees here a bit by decreasing the points extents. And now, as you can see, you have some flaws here in the difference of the points, just because the point extents are not really set up in an optimal way. So let's actually increase the points extents here to fix this. Yeah, that should do it. And then, of course, also we can spawn some assets on some points of the lake procedurally. But of course, this is way too many, so I'm just going to apply some density filtering. First, adding a density noise to apply some random density noise values to these points. And then filtering them out based on these values that were being set by the noise. Then we can also further modify the points by adding a transform points node. And again, add some random rotation and scale, etc. But we will go into more detail in all of this later when we build the actual forest environment. So this is just an example, and I wanted to quickly show you. Next, I would like to talk about point grids. With the help of point grids, you can create assemblies of assets around other assets. For example, you can use it to spawn a bunch of rocks around these trees, or foliage around other foliage, or all sorts of things that you can get creative with. All right, let's start by adding a surface sampler that will define the points that we want to copy our points grid onto. In this case, I need less points, so I'm going to increase the looseness of the points. And now we're going to create the actual point grid. We're not going to see anything for now. First, we need to change some settings. We're also going to create a copy to points node. And for the source pin, we're going to set the output of the create points grid. And for the target pin, we're going to set the output of the surface sampler. What this node will do is copy all the points that we define or that we create in our create points grid onto each of the points that we are creating on the surface sampler node. But in order to see it, we still need to change some settings on the create points node. It needs to be set to local and also local inverse transform, which I think just transforms the points of the points grid into the coordinate space of the surface sampler. Let's set the debug flag, and something is actually showing up here. To make it more visible what's going on here, we're gonna change some of the settings. I'm gonna add a transform points node after the copy points. Set its debugging flag. And set an absolute scale of 5. Then I'm gonna adjust the grid extents of the create points grid to something around 250. And actually I'm gonna adjust the extents of the surface sampler points, maybe to 25. And then further increase the looseness and maybe change the seed also. So now you can see that we are spawning these point grids around our surface sampling points. Now we can add a static mesh spawner and actually add some static meshes to these points. Adjust the scale again because it doesn't really fit for this kind of mesh. And then also apply some random rotation. And some density noise. And density filter. Now for the actual points of our surface sampler, we're gonna add another static mesh sampler, a static mesh spawner, and add some other assets, for example, a tree. Now this is a very basic setup for spawning static meshes around other static meshes, and we're gonna go into more detail for this kind of setup later on when we build the actual forest environment. Next, I would like to look into volume sampling. You cannot just use the PCG framework to spawn points on a landscape or sample points on a mesh. You can also use it to generate points in a volume in 3D space. For this, we are going to create a volume sampler node and debug it. Right now, it seems like the extents of our volume are completely filled with one single point, or at least we cannot make out the extents of individual points. This is just because all of the points have a full density of 1 at the moment and are being displayed as fully white. So in order to change this, we're gonna add some density noise on top of this. And as you can see now, you can see the individual points that are being sampled in the volume. Let's also add a density filter and increase the bounds here, the lower bound. And now, as you can see, you are randomly filtering points that are being spawned in this volume using the volume sampler, density noise, and density filter. Next, I would like to talk about mesh sampling. With mesh sampling, you can sample points on your static meshes and use these points to spawn other meshes on top of these. So we can create things like overgrowth or mossy patches on rocks, or as you can see here, these kind of money plants that are growing on top of this rock asset. To create this setup, we're gonna start with a node that is called create points. We are using this node to create a single point in the middle of our PCG volume. Just click the plus button in the points to create array and leave everything as the default value. Then also set it to local. Set the debug flag and you will see that in the middle of your volume, you will have one single point. We are now using this point to spawn a static mesh. To the static mesh spawner, I'm adding the static mesh of the rock. And I might also want to adjust the scale of the point. So I'm adding a transform points node in between. And now in order to sample points on this static mesh, we need another node that is called mesh sampler. Drag the same asset in the static mesh slot here. And if you look at the debugging now, you will not see any points on the mesh yet. And this is because the points that are sampled right now are actually being sampled in the origin of the scene. So we need to bring these points into the coordinate space of the single point that we created here. For this, we are using the copy points node and connecting the output of the mesh sampler to the source of the copy points and the output of the spawner to the target. If we set the debugging flag now, we will see that we are sampling all these points on our static mesh. We can change the sampling method. Right now it's set to 1 point per triangle, but it can also be 1 point per vertex, or Poisson sampling, which we can then further define here by setting a sampling radius to make it more dense or less dense, and adjust the settings according to our needs. I'm going to leave it at something like this right now. And now I'm adding a static mesh spawner after the copy points node. And I'm going to add a foliage asset here. Just going to drag it into the mesh sampling slot here. Okay, now as we can see, the foliage is spawned all around the rock asset, which is probably not what we intended. So we're gonna add a filtering node in between. We're gonna use again the normal to density. And just use the standard upwards pointing normal, add a density filter. And then connect it again to the static mesh spawner. Now we might also want to adjust the scale of these points here. And maybe something between 0.4 and 0.8. I also want to add some variation, so I'm just also putting some other money plant assets here. All right, and there you go. And this is a very simple example on how you can use the mesh sampler to spawn foliage assets on a rock asset procedurally. The last technique that I would like to look into in the first part of this tutorial series is subgraphs. With subgraphs, you can take certain functionality of your PCG graph and put it in a separate PCG graph, then reference this separate PCG graph in your parent PCG graph to create additional functionality or to outsource complicated part of your graph and make it more structured. For example, we can take this mesh sampling graph here and reference it in another PCG graph that is sampling points on the surface. To create this kind of setup, we're gonna start with the surface sampler node to define the points that we then want to copy our mesh sampling graph onto. I'm gonna increase the looseness here because we don't need so many points. And then I'm gonna drag into this parent graph the actual graph of the mesh sampling and connecting the nodes. Right now, you won't see much yet because there's still some changes that needs to be done to the mesh sampling graph. So let's jump into this graph. And for now, I would just like to disconnect the create points from the transform points. And I would also suggest you to click the cleanup button in the PCG mesh sampling volume to completely stop the generation of procedural assets. The reason for this is that we are now changing the way we are sampling points on this volume in order to prepare it for being used as a subgraph, and it would completely overload this volume with points, which leads to crashing. After you press cleanup, you can then just connect these two nodes, the input to the transform points, and you should see your mesh sampling subgraph being duplicated on all the points that we are sampling on the parent graph. And this concludes the first part of this tutorial and overview of the PCG framework. In the next part, we are starting in the new scene from scratch and building a forest environment using all these various techniques that we learned in this first part.